Okay, great. So, hello everyone who's watching us. So, thanks to those of you who watched the first couple of streams on this infracalculus, infrageometry program, and also welcome those of you who are new. We'll try to sort of make sure we don't assume too much background. So, certainly the first maybe 10, 15 minutes of the stream will largely be focused on just recapping what we've covered so far in the first two fairly exciting live streams on this particular subject. So just for those of you who've been to our first couple of these live science broadcasts will know that we're doing these with myself and with Carlos Zapata, who's also on the stream. But this week we also have a new institute fellow who's just been onboarded. And who Carlos and I are hoping will, amongst other things, work with us on this project and on extensions of it, and particularly applications to things like symplectic geometry, Poisson algebras, that kind of thing. So we're very glad to have Utkarsh Bajaj on the stream with us today. So Uti, do you want to say hi?
Hi everyone. My name is Utkarsh, and Jonathan, that was a nice pronunciation there. I have to say that. Also, I'm a student at the University of Waterloo, and I have been involved with Wolfram's physics efforts for a while now. And so I'm passionate about causality and simple geometry and mostly discrete stuff. So I'm looking forward to talking to these guys about how it all works.
Great. And as the kind of newest addition to this particular research project, the hope is that, well, part of our hope is that today, Uti, as someone who's kind of in the process of being onboarded and getting up to speed, will sort of be able to play the role of the kind of audience conduit, right? So as Carlos and I try and summarize what it is we think we figured out, and particularly what Carlos I think has figured out over the last week or so, the hope is that Uti can jump in and kind of ask the obvious questions or point out places where things we say don't make sense, or where we're missing kind of important conceptual steps or whatever. But okay, so with that, let me at least start by sharing my screen. And how do I do this? There we go. Okay. Right. Okay. So this is the notebook that we prepared last time, where we were really trying to formalize some of the kind of ideas that we threw around in the first stream. So, for context, those of you who haven't tuned into these before, what we're trying to do is we're trying to kind of build up a new foundation for what we call infrageometry, where the idea is to kind of, in some sense, to take, we've got continuous differential geometry that's been well studied for well over 100 years. We've got discrete differential geometry that's relatively new, but which is a kind of, which is a field in its own right, which has largely been concerned with taking sort of continuous smooth manifolds and constructing things like CW complexes, simplicial decompositions of them, and then seeing kind of what can be reconstructed from that discrete combinatorial data. What we're really trying to do with this infrageometry program is develop a kind of robust mathematical theory that underlies these two approaches, to develop a kind of a sub-geometric theory that consists of all the elements of geometry that don't care whether the underlying space that you're dealing with is continuous or discrete. That's kind of the broad philosophical objective. So what we've been trying to do so far is to kind of is to go down to the level of graphs and hypergraphs and figure out how we might be able to build up all the standard machinery of differential geometry, from tangent spaces to tangent bundles to to vector fields to tensor fields and so on, up from those first principles. So here was kind of here was really how we left things last time. So the idea is, if you take just an ordinary graph, an ordinary undirected graph, it is a topological space, right? Every vertex, if the vertex set is a point set, every vertex has a collection of neighborhoods that are, the connected subgraphs that contain that vertex. But actually, it's more than a topological space. It's actually a metric measure space, because every graph is sort of trivially a metric space, because you can take any pair of vertices, any pair of points, and you can compute a distance between them by just evaluating the minimum number of edges that one has to traverse when moving from one vertex to the other. It's also, by extension, a measure space, because we can equip it with an analog of a Riemannian volume measure by looking at essentially discrete geodesic ball volumes. So in other words, we can look at any vertex, we can grow out a subgraph consisting of all vertices that exist within distance n of that vertex, and we can equip that, and we can just count the cardinality of the vertex set of that subgraph, and so we can equip that graph with a kind of trivial counting measure. So we immediately get a kind of a sort of metric measure space. And so within the context of the infrageometry program, the idea is that the underlying undirected graph represents the metric, so the edges give us sort of the metric structure. And then on top of that, we can then define directed edges that essentially tell us, how we can move through that graph. And the idea is that the intuition is that the directed edges we kind of impose on top, those are the analog of our connection. So in the simplest case, we could take a metric connection, something like a Levi-Civita connection, which would just be we start from an undirected graph, we start from a metric, and then for every undirected edge, we just replace it with a pair of directed edges, one going in each direction. And so now these directed edges tell us precisely how we are able to move around this graph. But we could also, in the more general case, we could imagine equipping the graph with a kind of more complex set of directed edges. Maybe not replacing every undirected edge with a pair of directed edges, but choosing a kind of distinguished direction or something. And the intuition is that this would kind of be the analog of a more general affine connection. And then the statement of kind of metric compatibility, the statement that the connection we defined is compatible with the metric, and therefore that the covariant derivative of the metric tensor vanishes, becomes the statement that the directed edges we impose on top respect the structure of the underlying undirected graph. That's I think the first non-trivial statement. So maybe Uti, if you have questions or comments or remarks on that, let us know.
Sure. I mean, till now it seems, it's a bit counterintuitive at first. So, I mean, just to clarify, you have the undirected graph, and so the metric is the combinatorial metric, right? Like the shortest distance between them.
Mm-hmm.
And so, I mean, if you look at it from a more physics point of view, if you're trying to define a connection, like so you're trying to go from one point to the other, essentially, right?
Exactly.
Transporting a vector or something.
Right. And so in particular, for the purposes of connections, you want to have directed paths, right?
Okay.
Because you want to be able to say, I'm going from this vertex to this vertex.
Right.
So our kind of initial intuitive idea is that we want to have some way of replacing these undirected edges, which just tell us about distances, with directed ones that tell us about directional paths.
Yeah, okay. No, that makes sense. Okay, yeah, and the most trivial connection, or like the nicest connection, would be that every undirected edge is replaced by like back and forth ones.
Exactly. So this and crucially, and the directed edges are kind of weighted equally in both directions. And so this would be the analog of a Levi-Civita connection. If we imagine something like this, where the weightings are not the same necessarily in both directions, so the distances are induced by the connection are not necessarily equivalent between A and B and B and A, then this is still an affine connection, but it's not. This is still a metric connection, but it's not necessarily Levi-Civita. And then we could also imagine even more than that. We could imagine just removing. We can imagine having directed edges that are added that don't necessarily respect the underlying undirected edge, the underlying undirected graph structure. That would be an analog of a non-metric compatible connection.
Right. Yeah, it makes sense. Thanks.
Okay, cool. And then so then the fundamental theorem of Riemannian geometry translated into this setting just becomes the statement that there is one unique choice of directed graph that preserves the metric of the underlying undirected graph, and therefore that the Levi-Civita connection is somehow a unique metric compatible connection. Does that make sense? Okay, cool. So, all right. So now we've got a connection. Now we have some way of defining tangent spaces. So the idea here would just be to say, we pick a vertex like this green vertex down here, and we can literally just look at what are all of the outgoing directed edges from that vertex. And that gives us, so we just kind of effectively define these as being the tangent vectors. We define this, and so we define this particular collection of edges as being the tangent space at that vertex. Now, as we kind of discussed, as Carlos and I discussed last week, it's a little bit arbitrary to just say that we're looking only at edges. We can, in principle, say we're looking at directed paths of a given length. So, so this here is an example of all the directed paths of length 2, also highlighted in red. So this is just as good. This is an equivalently good definition of the tangent space at this point. So in some sense, one has freedom to choose how large one wants the tangent spaces to be by just choosing, how long we want the directed paths emanating from that vertex to be. And then, just as it should be intuitively from the connection to differential geometry, the connection, i.e. these directed edges, tell us how the tangent spaces change as we move from point to point, right? So, okay, does that part make sense?
Yes. How do you like, what's the formal way of proving that these definitions are equivalent? Or
Well,
like
they're certainly not equivalent, right? I mean, so it's not even, because it's not, well, okay, let me rephrase that. It's not clear to me what it would mean to say that the definitions are equivalent. What we're trying to do is I guess define a set of definitions, or is to give a set of definitions which somehow preserve the logical structure of the corresponding definitions in continuum differential geometry. And precisely what that means, I mean, this is in a sense, this is one of the things I hope we will end up discussing today is, because the way I'm increasingly thinking about this, and Carlos, I know you'll have comments about this, so I'll let you field this question in more detail. But kind of the way I sort of think about this is, is in terms of a sort of functoriality and or commutative diagram type story, right? So we've got, you can do operations in continuum differential geometry. And then we've got this operation, which is, discretizing, which is, passing to a simplicial, doing a simplicial decomposition, passing to a CW complex, doing some kind of triangulation of the manifold. And then, so then you're in the discrete world, and then you can do corresponding operations in the discrete world. There's also an operation that takes us back again, right? So you're doing operations in the discrete world, and then you can take some kind of limit as, as your edge lengths go to 0 or something, and that translates you back into the continuous world. And so what we're trying to do in some sense is the way I'm increasingly thinking about this program is we're trying to sort of define a set of operations in the discrete world such that when we do that transformation that takes us to the continuum, i.e. taking limits, or that takes us from the continuum back, i.e. doing decompositions or doing triangulations, that we preserve kind of the compositional structure of what's going on in these two directions. So we're somehow wanting to define a set of operations that makes these two transformations, the transformation of discretization and the transformation of limit, of taking limits into functors or into things that are as close to being functors as possible. I don't know, that would at least be, so we're, in a sense, that's the condition that we want to apply to our definitions. We want we want to choose appropriate definitions in both of these worlds that sort of somehow maximize the functoriality of these two transformations. But Carlos, I don't know if you'll certainly have other things to say.
Yeah, no, I'm building on that. I think you asked the right question, and I think a lot of people in the audience might be having the same question. What does it mean? Why do we call this a tangent space to begin with, right? This is not tangent to anything, and it's not even clear that we're gonna call back to differential geometry in an explicit way anytime soon. I think this is kind of placing the goal at the end of the course in some sense. Like we want to have a way to identify these formalisms under a sort of a larger framework where they are effectively indistinguishable, and this is where the categorical perspective perhaps is the most useful, because if you end up the categorical or algebraic perspective could be the most useful. So I will reduce it to a very concrete question, which is kind of what motivates the short presentation that I will do in a bit. But basically, if you manage to find some mathematical feature that is operational, meaning that you can, as Jonathan said, had some kind of logical deductions from it, or use in a computationally active way, so it's not just some inert fact, it's something that is operational, and that is in common between a construction on finite sets and graphs and so on, and this infinitary, smooth, continuous topology kind of setting, then in my opinion that's a valid sort of success state, right? Where we've managed to capture effectively those aspects of the continuous theory in a purely finitary and discrete setting, right? And I think to make a more philosophical point before we get into details, when you study differential geometry, you actually and differential topology, and when you're learning mathematics and maybe in a math degree or a computer science degree, you actually deal with finitary information all the time. Although your spaces are infinite and continuous, and the cardinalities of the sets are technically infinite, and all those kinds of things, you hardly ever deal with infinities, right? Like you are always thinking about finite numbers of things. In fact, small numbers of things. Usually, you have like maybe two vector fields that are behaving in this way, or I have a surface that has this countably many singularities and such. So all these objects are always very finitary. When you think about the homology groups, all these things, they tend to be finite groups. These are all quite discrete, finite objects that help you encode the information of otherwise smooth, continuous shapes and geometries, right? So in a sense, what we're trying to do here is, as Jonathan mentioned, is to somehow go under the hood and identify those patterns at a level that doesn't require that doesn't really play the topology game, because the topology game has kind of consistently been abstract, make some clever construction in your geometry so that you can capture things in a combinatorial or algebraic way, and so that combinatorial and algebraic structure is going to classify things. And I'm talking about homology, I'm talking about all the techniques that everyone is aware of, and counting curvatures and things like that can effectively classify in some sense your spaces. So we are trying to do something similar, but with features that are in some sense more fundamental. So for example, in what I will describe in a bit, we just focus on the concept of path and function, right? And path and values. And so just with that very core concept, you're basically asking how much can you construct, how much can you get for free, just by assuming that you have something that is at least morally like a function, and morally like a path, morally like a vector, and things like that. And so the hope is that you can get a lot, and some would hope everything, but I don't know if we are ready to go as far as saying everything, but that's a little bit the sort of the context of that particular question.
Just to clarify a few things. So I mean, building on Jonathan's point,
Yeah.
like the categorical perspective and stuff like that. So I think right now, if I ask you the question, like, what are the elements of the tangent space, it won't necessarily be a good question to ask, because right now you care more about the functions or the maps between different objects. So I mean, I think I don't know if this is how you actually thought about it. The reason you define the tangent space is this, like, I don't think you actually care about the linearity and stuff like that, right? You just want to capture the essence, which is like it consists of all directions, like outgoing directions.
Exactly.
And you can easily define like projection maps as like the thing which goes to the point, because it's the place from which the edges are originating.
Right.
And so is that the thing, the mindset you're using?
I think so, but I would also say that the extent to which which concepts like linearity are preserved in going from, say, continuum to discrete, I would say that's still an open question, right? That's one of the things that in part this program will be trying to establish is like, does it still make sense to talk about the kind of linear algebraic properties of these tangent vectors when one passes to a very, very finitary structure? There are various problems, like, so we went some distance towards trying to figure out how this might work in the first live stream of figuring out, how might an inner product work, right, etc. How might we be able to turn these tangent spaces, these locally defined tangent spaces, effectively into Hilbert spaces, or into things that that discretely resemble Hilbert spaces. But how successful that will be, I think we don't know. Would be my
just to preface a little bit what is coming. I would say that you have to ask yourself hard questions, like what is addition in this context, right? So when you have something like linearity or additivity, you basically are asking, okay, so what is addition? What is summing? What am I doing when I sum? And effectively, when you're doing when you sum, is that you spot that your compositionality structure of choice is commutative and associative, basically. And if there's a multiplicative one, it's going to distribute over that one. And that's the context where you say, okay, I found an addition. I'm dealing with something that is additive, and that is certainly there. So the notion of path composition, for example, it's an abelian groupoid in the sense that at least the paths through a point in your graph, these are abelian groups. They have this you can go back and forth, and it doesn't matter which order. So in that sense, an abelian group is very close to doing addition. It's not literal addition of a field that you already know, or in a ring that you already know, but it is algebraically indistinguishable from it, right? So and it does what it's supposed to be doing, which is there's a 0, which means stay there. There's a +1, which you can iterate, that is going to take you to all the places in the future, and you can effectively run backwards if you needed to. I mean, running backwards actually in this context is probably much less desirable. So you probably want to always work with semi rings and semi groups and so on. But anyway, it's just
I don't think it's even clear right now that we should look for linearity, because maybe it's just that when we take the limit, you get some correction terms which vanish or something like that, right?
So actually, I want to make the point, just sort of to restate the functoriality point in less category theoretic terms. So what we want to do is, when we talk about, when you asked initially, how do we know these definitions are equivalent? I guess the notion of equivalence is more like we want the results in one setting to deform in a predictable way when we translate them into the other setting, right? So in particular, like, okay, suppose we take a continuum geometry like this, right? We take some hyperboloid and we discretize it, either by doing a triangulation or this kind of Poisson-based process or whatever. Suppose we looked at some properties of the tangent space in the continuum geometry at some point, and we proved something about that particular tangent space. Now that particular result obviously won't hold in general when we go to the discretization of that, and we translate it to kind of to the discrete surface surrounding the same point. But ideally, if the infrageometry program is successful, there should be some way of directly translating the result that we proved in the continuous case into one that holds in for the case of the discrete tangent space in some predictable way. So as I say, you can work in the discrete setting, then take a limit, or you can work in the continuous setting and then do a discretization, and all your results should translate in some fairly direct or deterministic manner. So it's a lot like, one of the ways I would think about it, or that I tend to think about it, is if you think in terms of, say, representation theory, right? So representation theory is some deep set of functorial correspondences between, the category of some algebraic structure and their homomorphisms and the category of vector spaces and linear isomorphisms of those vector spaces. And so it's not the case that, you just directly take some theorem in group theory and it applies to linear algebra. But the whole idea with representation theory is that it gives you a kind of set of, it gives you a bunch of mathematical machinery that allows you to translate some statement about some algebraic structure into a corresponding statement about actions on vector spaces, or vice versa. And so what we want to do is kind of some analog of representation theory, but this time giving us a functorial transformation between kind of continuum and discrete geometries, amongst other things. I also want to re-emphasize actually the point that Carlos made. Carlos made this offhanded philosophical remark, I think, last time, kind of about philosophy of mathematics, that I think is, that I at least really like, because it's a nice way of kind of encapsulating what certainly historically the power of mathematical formalism has been, which is to take these infinite these infinitary structures and be able to kind of reason about them in finitary terms, right? So Carlos made this point that mathematical notation, it's all finitary, right? We use a mathematical statement is a finite sequence of symbols extracted from some finite symbolic alphabet. And yet, we kind of set up the formalism in such a way that, those sequences of symbols in general give us a formal way of reasoning about objects that have no finitary representation. And so it's in a sense. Therefore, I think that gives us a kind of nice philosophical grounding for the infracalculus program. Because what we're really trying to do is kind of somehow go beneath sort of the standard approach to doing mathematics, where so now we're trying to develop a language which fundamentally doesn't care whether the structures we're dealing with are finitary or infinitary. The kind of the underlying symbolic representation should be the same, or as close to the same as possible. Okay. Did you have Uti? Did you have any other comments or remarks or
No, yeah.
Okay, cool. So just I think we're mostly we're mostly done. We're not claiming to have figured out a huge amount yet. But so then the idea, okay, so once we've got tangent spaces, then we can consider a tangent bundle. We just take a disjoint union of those tangent spaces, just like we would in differential geometry. And so so actually, nice, very, very nice. Once we have this definition of tangent spaces, everything else, all of the other definitions that we came up with last time are really just very, very direct translations of standard differential geometric definitions, right? So the tangent bundle is literally just the disjoint union. It is, it's exactly the same operation. Smooth sections work in exactly the same way, right? So anytime we take a smooth section of our tangent bundle, we are literally just selecting one directed edge from each element in that disjoint union. And so then this is an example of one of those smooth sections. So if the correspondence with differential geometry is correct, then this should basically behave like a vector space, which it does. I mean, so again, just kind of instinctively, intuitively, what this is every vertex in our graph has one outgoing edge, one outgoing arrow. And so that feels very kind of that feels very vector field-y in some sense. And then so rank 2 tensor field would be every vertex has 2 outgoing directed edges, etc. And so as an example of one of those, I mean, we didn't get to formalizing that last time. Maybe we'll get to that this time. We came up with where was it? So this is an example of one of our tensor fields. So this is us computing sort of angles between between pairs of tangent vectors, effectively defining a sort of inner product structure where the idea is, I mean, this is Carlos's sort of suggestion. Again, it's a very, very direct translation of the way we define inner products and angles in standard, within a standard tangent space. Is just, you take a pair of the tangent vectors. If the endpoints of those tangent vectors are directly connected by a directed edge, then we say that the angle between them is 0. Otherwise, we say the angle between them is is pi or 1 or something like that. So in a sense, they're at the level of an individual edge, there are 2 possible values of the projection, 2 possible values of the inner product. Either they are parallel, the projection is 1, or they are or they're orthogonal, the projection is 0. And then the idea is, as you grow out progressively larger curves, then you allow for a progressively larger range of values of those projections. But then, so this would be an example of now a rank 2 tensor field. Then the rest of the time, I think we mostly spent talking about directional derivatives and covariant derivatives, which is what Carlos is going to be talking about in just a moment. So I won't discuss that. But okay, so with the exception of derivatives, I think those were the main points that we covered in the last couple of live streams. So before we launch into Carlos's discussion, does that sort of make sense so far?
Yes, yeah.
So so this picture of a vector field as a smooth section of the discrete tangent bundle we defined before, is that all sort of comfortable?
Yeah.
Okay, great. So in that case, unless there's anything that you think I've missed, then I think we can hand over to Carlos.
Yeah, thank you very much. I think it's sorry, I didn't know if that was a question. So yeah, it's a very good segue from where you left it, because we had these examples of tangent bundle and so on, and it's basically what motivated me from those sorts of questions to go into this. So let me just join with my Blackboard. So I'll do a little mini lecture on these structures that have popped up, but I want to motivate exactly. I think it's very pedagogical and it's very good for illustration to have to show the way in which we arrive at this particular structures and how you normally define vector
Oh,
fields.
well, sorry.
Yeah.
I didn't even notice there was a waiting room.
All
Sorry.
right. Yeah, no problem. So, okay, let's see. Share the screen, whiteboard, share, hide the stuff. Everyone can see that, I imagine. And I'm going to go on tablet mode. Okay. So, I want to talk about finite difference operators. And so this is one way that people in the audience could think of what I'm going to talk about right now is imagine you go to your calculus class and they start to explain the notion of a derivative. And, they say, we're going to take a function, we're going to evaluate it at this point, and we're going to see what happens when we evaluate it at this other point, x plus delta x, and we're going to now look at the delta of f, what is the difference in function. That's normally what precedes the discussion of derivatives by taking the limit when your displacement is infinitesimally small. So finite difference operators is basically if you don't want to go there, right? Like imagine that you don't want to take limits, you're sort of, this is way too fancy, this is too modern mathematics, I just want to stay with arithmetic. That's basically finite difference operators. So we're gonna essentially go back to middle school mathematics, but with a higher mathematics perspective on them. And so okay, so what is the motivation for this? So remember that Jonathan just outlined the concept of what we think should be a discrete notion of a tangent bundle. So so the plan, by the way, is we're going to talk about a brief motivation from Jonathan's presentation. We're going to discuss something called weighted derivations, which is this thing I say it's like doing differential calculus without taking limits. And then we're going to see if there's some analog of the Lie bracket of vector fields, which is sort of a hallmark of differential geometry structures in this context. Udi, you have a question?
Yeah, I got a question as soon as you said tangent bundle. So essentially in the tangent bundle, you have like if you use the second definition of where you take paths of length 2, then when you take the disjoint union, are you like labeling the paths differently with some other parameter, like some other variable, when you take the disjoint union, or is it just the same edge that?
Yeah, I think so, because I mean, so this is Carlos, I'm curious to know what your perspective on this is, but this is a problem that one faces in the discrete setting when one tries to do discrete differential geometry that doesn't really occur in the continuous setting, which is the kind of the case of collision, right? So collisions between paths are much more common in a discrete space than they are in a continuous space, and so whereas. So yes, because when one takes a tangent bundle, when one constructs a tangent bundle, one is necessarily taking a disjoint union. One has to worry about it, so inevitably the same paths and the same collections of edges will appear in multiple tangent spaces, and so one has to be careful to make sure that there's an additional labeling parameter or index parameter that's used to distinguish between them. That each bucket in the tangent bundle, so to speak, doesn't just contain this path. It says this is the path, and this is the particular bucket that it belongs to. Right. That's a problem that we just for sort of historical context or whatever. That's a problem that we face a lot when trying to do in the kind of Wolfram physics context. When we're trying to do for kind of general relativistic purposes and things, we're trying to reason about geodesics. You get this phenomenon that happens in discrete space that just doesn't happen in continuous space, which is that you can have geodesics. You can have collections of paths that just kind of happen to collide with each other, and then they kind of stay collided for a while, and then they separate again. Right? That doesn't really happen in a continuum geometry because the probability that two paths are going to intersect kind of over any non-negligible distance is zero. Once you're in a discrete setting and you have a countable measure, that probability is non-zero, and so that you get these issues of like incidental collisions of structures, incidental collisions of edges and things, which don't really have a direct continuum analog.
Yeah, so my comment on that is that it's actually similar to the continuous case of affine spaces. If you think of your vectors as oriented segments on an affine space, which in some definitions, in some formalizations of affine spaces, you shouldn't do that because those are not vectors, those are oriented segments, and they're not the same thing. But if you were to think of them as oriented segments of your affine space, which is certainly something that intuitively some people think about, then you run into that problem because obviously, the vector from x to p is the same as the p to x, it's the same segment, right? So what's crucial here is that you're not going to have once you have a vertex, the collection of outgoing edges from that vertex, that's a well-defined set, and those because they are outgoing, right? They are not going to be edges of other tangent spaces, right? So in that sense, there is no ambiguity there. But again, it might be that the formalization requires different layers. In fact, I was going to talk about that precisely to motivate. So let me just use the diagram that I have on the screen to go on this. So imagine that. So we begin with the analogy, the discrete geometry analogy, where M is some set of points. So we're gonna think of this as discrete set of points. So this is in a vacuum, right? They are not embedded in any space. They are just discrete set of points. And we're gonna think of a graph structure, right? So this is a connectivity structure. Let me call it G for graph. So this is an undirected graph. On M. So very evocative name G, by the way. So something like this, right? You could imagine you have some undirected graph. And so the idea would be that once you have this graph, which gives you a notion of connectivity between the points of the quote-unquote space, you immediately have, you can ask the question, okay, imagine that I place myself on P, right? So you can ask, okay, where can you flow out of P and reach somewhere that is connected? So that's, the length one paths from P. So you have this directed edges, and they are directed because you are saying P is first. You're saying I am living in P and I'm going on a journey somewhere else, and that's why they should be directed. So that set, which is induced by the structure G, that should, in principle, be TPM, right? That collection. So, those. I'm going to be very schematic here, so I'm going to use drawings. So I hope that makes sense, right? That's going to be your definition of a tangent. Of a tangent space, right? And again, these are all evocative names. We're not trying to make any formal claim yet. Okay, so then the question is, well, one important point. So I'm going to make a remark because this will be for later discussion. So remark, not so much the exposition, but it seems that G induced. G induces several things. So it induces connectivity, but also metric, which and connectivity itself induces. Let me put it like this: G. Don't need so many words. G induces connectivity, and connectivity induces tangent bundles. Tangent, yeah. So this is something that is quite unique to the discrete case, apparently, because in the continuous case, you're familiar with, you have a manifold that is some kind of topological space that is sort of devoid of geometry, and you sort of infuse it with geometry by saying, I'm going to put a metric on top. And by the way, this perspective I've always found quite artificial, and It is mathematically sound, obviously. I mean, that's how we do things. But if you think about it, it's actually very counterintuitive. The fact that you can think of what is S2 as a differentiable manifold, right? What is the sphere? Just the sphere, not with the metric, right? That's a very weird thing to think about, right? Like it's not. I mean, you have to resort to your technical definition. Okay, it's the equivalence class of topological spaces that have all these atlases, blah 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 blah. Like you have to resort to that and have a picture of, okay, it's all the classes of the formations of this particular example of a topological blah blah blah. It's like you need some kind of concrete technical definition to do it, because if you actually abstract the metric structure from a manifold, you're not going to have a good intuition of what a manifold is to begin with, right? So I think what the discrete case is telling us is basically that story in a very packaged way. It's telling you, the same graphic information that encodes connectivity is also naturally encoding metricity, is also naturally encoding what allows you to define as paths, which by some notion of sequentiality, you end up with something like tangent vectors and blah, 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 right? So just as a warning here that the discrete setting is making things more explicit than in the continuous setting are a bit more abstract. Okay, so what about functions? Okay, so the other basic idea, so this is the idea that you can move around your manifold and you have paths. So the shortest paths are the tangent space of the point. Now, you want features on your space, right? You want the space to have inhabitants in some sense. You want some kind of features in the landscape, and features in the landscape are functions. So you're gonna think of assignments from, I'm just gonna call it F, which is the set of all assignments from little f from M to some field. And here a field is going to be, field of numbers. So what that means is you can do, let me put it this way, f with a plus and a times. So you can do addition and multiplication, and this might be f2 with only two elements, like a Boolean numbers, or this could be z, or this could be q, or this could be r. Principle, I'm gonna put f. And so this is basically the answer of a feature. I am at this point, and the temperature is whatever x, right? Some element in f, or the mood in this town is y, an element of a field. We all know that mood is taking values in fields, right? So anyway, the idea is, okay, you traverse your manifold and you see the features along the way, and you basically you build a story of what you see, right? You say, well, I was in this part of the valley, and there was like green pastures, and now I'm high up in the mountains, and there's this and the snow and whatever. So to measure the change and to tell a story, you need to basically say, well, I was here first and then I went there. So the basic, most minimalistic definition of a change in traversing a featured landscape is to say, well, imagine that I'm in a point P in my discrete manifold, and I go on a path that involves going over an edge to another point Q. Imagine that there's a function f on your graph. So this is a graph. It's connected to other points, etc. And there's a function f that is taking values over f, like I say. So what you can ask fundamentally is, they say, okay, so f has changed. So the change of f evaluated. So I'm going to denote it like this: the change of f from P to Q, right? And let's say that is evaluated at P, but I don't need more notation in this context because P and Q are already specifying that. So P and Q are an oriented edge. And so this is, as you can expect, because F has, so the field has values, you can just evaluate at your endpoint and take the difference in your starting point. Okay? So this, so by the way, when F is a field, your curly F becomes a ring, right? So, or in fact, it becomes an F algebra, an F commutative algebra. So F here is an F commutative algebra. Let me say commutative, otherwise sounds weird. It's a commutative F algebra. And the definition of addition and multiplication is pointwise, meaning you give me two functions, I can do f plus g by taking a point x, and I do f plus f of x and plus g of x. If you give me f times g of x, I just evaluate each of the values and I write it like that. No problem. Okay, so the idea is that when you define these operators, this finite difference operator, these are very natural operations in F. This is for any delta PQ. Sorry. This is just the difference defined at P and Q. Okay, so this gives me a number at a location. So if P has only one edge specified, let me call that x of P, right? It's just a name for the edge that it points to Q. Then this number, the delta PQF, is a value that depends on the point P and the direction xp, right? So if you had an assignment of such xp's for all p's in your M, so if you had xp for all p in M, right? You have an assignment of single elements like that, then you can define something that I'm going to denote this way, delta of x of f, right? So how do I define this delta of f of x? So I'm going to define it as a new function. So you give me function f, you give me an assignment x of edges that way, and I'm going to define this element as, well, you just take x evaluated at p. So you evaluate xp, which gives you some pq edge, directed edge, and what you do is just the difference. You evaluate f. Okay, let me put it this way. Xp, sorry, xp of f, right? It sounds like a very redundant definition, but if you look at what is on the screen, that's what it does. So this basically does f evaluated at q minus f evaluated at p, where q is coming from the fact that x evaluates, it's the head of x, right? That's the meaning. Okay, so this turns the operation delta x into a map that sends any function to any functions, and it does so in an f linear way, right? So this is a very natural operation. I mean, we're effectively recovering something that looks like a vector field because we are assigning a direction to every point in your manifold. So it might be the discrete analog of vector fields, and that's sort of where we're going. And so, okay, how would we be convinced that this is the discrete analog of a vector field? There can be many answers to that, and a lot of people might be satisfied with a picture that, oh, yeah, you give me a finite set and it has some arrows coming out of every point. So if I assign one arrow at each point, that is like saying, yes, I have a tangent vector at each point, I have a vector field. Okay, I personally would not be satisfied with that because that's a cartoon of a vector field. A vector field has a lot of a structure that is usually sort of kept behind the scenes, and it works and it sort of conspires so that you get all these nice algebraic structures in practice, right? And by nice algebraic structure, I mean that you have a C-infinity module which has this Lie algebra bracket of which you normally define as the commutator flows and so on. Okay, so the question is there an analog of such an algebraic structure? Because vector fields otherwise just feel like, okay, these are nice operations that have this C-infinity module structure, and let's see if there is something like that. And so the question is, do they behave with respect to the commutative algebra of functions like a special kind of operation? So they are F linear, but how do they? So that means that they are additive in particular. So it's easy to verify by definition. I mean, this is basic arithmetic, that if you take the finite difference operator of f plus g, you just get the sum of the two. I mean, this is just a super trivial exercise for anyone in the audience. And if you take this, you know, r being some f element, this is linear in this way, right? This is very easy to check. That's what f linear means. Now the question is, what happens when you take the product, right? What happens when you do f times g, right? The pointwise product. In manifold theory, what happens is that you get the Leibniz rule. You get the product rule. Everyone is familiar from, you know, calculus in high school. You get product rule. So that's, you know, people, you know, in algebra that we call them Leibniz rule. And so the Leibniz rule will be written something like this. So we'll get delta f dot g plus f dot delta x g. However, when you do the computation, and it's a very short computation, it's really, you know, 2 lines long, you don't quite get this result, but you can modify the expression to recover these 2 terms, but then you get an extra term which looks exactly like this: delta f and delta g. So remember, delta x applied to f is a new function. So when I write dot between them, I'm just multiplying them as functions, and we write plus between them and just adding them as functions. So this is the particular axiom that this thing satisfy. And when I found this, which you know, in the first live stream we did this computation, and I was actually neglecting by sheer muscle memory of neglecting quadratic terms. I basically didn't see that this was not in fact the exact Leibniz rule, but it was something a bit more extended. So this is the natural axiom that satisfies. So it turns out that this is called a weighted, or let me say a weight 1 Leibniz rule. Okay, so the good news is we have literature that knows about this, and we actually have research that has been done on these kinds of structures. The bad news is not much is known about these things, and they fail miserably to behave algebraically, right? So usual derivations are very nice. As a very quick recap of usual derivations, if you have a ring, so recap of derivations. So if R is a ring, let me say R is a ring, you define the derivations of a ring. There R is defined as the set of all D maps from R to R, which are additive, and they satisfy Leibniz. And again, Leibniz is exactly what you know, it's the product rule. D applied to AB is DAB plus ADB. Okay? So these derivations, let me just write it very quickly here. AB equals DAB plus ADB, just for reference. So what there R is a R module. It means that you can multiply, it means that D plus D prime is in derivation of R. It means that R dot R is in derivation of R. Okay, that's very nice. So these are basically like vector spaces for those unfamiliar with modules, like vector spaces over rings. And rings are just like fields, like number fields, but that you can divide all the time. That's the only thing. So and most crucially, what happens is that because these are endomorphisms, you have composition of endomorphisms. So you can ask what this thing is. If I give you 2 derivations, D and D prime, in their R, you can compose them because they map R to R, so you can do one and then the other, so you can apply them to elements one after the other. So this turns out to, in general, not be in the derivations of R. The composition of derivations is not generally a derivation, but the commutator of derivations is a derivation. So if you are clever enough, or you struggle with you're exploring inspecting your expressions and saying, oh, what do I miss in this term to complete this other term, you can actually come to the conclusion that when you do this operation of derivations, which we call the commutator, which is basically composed in the two possible orders and subtract, this now is in derivations of R. Okay, therefore the derivations of a ring together with the bracket, the commutator bracket, is the canonical example of a Lie algebra. Okay, that's the shortest path to find a Lie algebra if you know about rings. Okay, so what happens in the discrete setting? Well, we don't know. that's the short answer. The exciting news is that we know that these things are weighted derivations, and so the reason why I wanted to have a self-contained presentation on this topic is that the question is, can I find an analog of this expression here of the commutator, so let's put in red question. So the question is, can I find, before question. So okay, so this was recap of derivations. So weighted derivations. You replicate the same the same definition, but you include a weight. So lambda is an R element, okay, and I'm going to define the lambda there of R as the same thing. So these are now the R to R maps that are R linear. Sorry, they're additive. We are just in rings, and they satisfy lambda Leibniz, I'm going to call it. Leibniz. And what is lambda Leibniz? Well, it's Leibniz. So delta AB is delta A times B plus A delta B. But then it has a lambda weighted term, which is sort of quadratic in the derivative, right? So it's delta A delta B. Okay, so these are weighted derivatives. So the question is, in general, for lambda not zero, lambda there of R fails all of the above. So all of the nice properties that it forms an R module that you can close under commutation and so on, that all fails for lambda non equal to zero, right? So the question, and this is where the actual open question is, given delta prime lambda derivations, so when I say lambda derivation, I mean generic lambda, so in particular non-zero. Because obviously, I think everyone sees clearly that when lambda is zero, this term vanishes and you get back to derivations. I mean, maybe I should remark that here. Sorry, let me just move. So if you have 0 there, R equals there, R, right? That's just a notational convenience. So given two generic weighted derivations, is there a operation, let me call it bracket like that. So yeah, let me say bracket with this, angles that goes from lambda there squared to lambda there. So, well, it's there. So sorry, yes. So to put it more explicitly here, whether we can find some construction that makes this into lambda there, right? So something that depends on delta and delta prime, that is to say that is going to be built out of compositions, additions, subtractions, some weightings or something. I mean, you can use lambda, certainly each delta has a lambda, and you can use that element of the ring to create an expression that, when composed, gives you a new unique derivation, a new unique lambda derivation. So it might well be that the lambdas, the weights, are ring elements. So it might well be that there's compositionality on the weight as well as the derivation, so to speak. So there's a sort of a ring endomorphism part of the data, and there's a weight part of the data, which has these two components. So it might well be that this composition requires to multiply or add weights in some way, and so on. But that's the open question. We don't know if this if such an operation exists. We know that for lambda equals 0, that operation. So just to again be super explicit, so if lambda equals 0, then this angle bracket is the commutation bracket, right? But this is just for lambda equals 0. Now the question is, in general, can we find so for people to have an idea of what I'm talking about, this is to say that I will write something like this composed with delta plus lambda, delta minus delta composed with delta,
It's stuff like a deformation of Lie algebras, and I think that has been looked at before. You have this initial Lie bracket, and then like in general, algebras can be like the deformation of algebras looked at using these Hochschild homology groups. And
Yes.
for Lie algebras, you can do the same exact thing,
Yes.
where you can deform a Lie bracket into like something like a power series in terms of lambda.
Yep.
So that when you said lambda is equal to 0, you get the original thing, and the existence of such brackets, I mean, which I think should be called it's called a star bracket, which
Yep.
is the analog of a star bracket, is just dependent on whether the whether the cohomology groups essentially, like whether they're like trivial or not essentially. I think this has been done before. I might be wrong, but
No, but this exactly. So this was what we briefly mentioned before coming online. So this is where deformation theory might come into place, right? Like so this is where, I mean, you might. This is a subtle game, because in the discrete setting there's no weight. Or the weight is just 1 and there's no option. I mean, it's a sort of a variable ranging over a single element set or something. It's only 1 that you get in the discrete setting. So it would be very informative to know what this deformation theory, and I am personally quite unfamiliar with deformation theory. I know what it's about and what it does, but I'm not super familiar myself with it. So that would be one path. But just to finish the train of thought here, and to conclude, the idea is that maybe you can cook up something like this, and like Udi was saying, and then you put well, technically there should be some term over here that looks like that, plus lambda squared of lambdas, whatever. And the idea is that when you set lambda equal to 0, then you recover the bracket, right? So this bracket depends on lambda, and then when you put the lambdas equal to 0, then it sort of kills off terms, and you get just the commutator. So the reason why this particular structure, okay, so as a concluding remark, you might say this is an artifact of the fact that you have a finite set, you have a graphic structure, you've been obsessed with this finite array program, and you want to be sort of a constructivist mathematician, and you don't want to use any infinite sets and so on, and you're dogmatic about it, and so that's why you're encountering this ugly algebra that is a non-Lie algebra. But actually, this structure is exactly what you obtain in the smooth context, in the continuous context, when you try to think about continuous difference, with finite difference in the continuous setting. So in that setting, so now change of gears very, very quickly, M is a smooth manifold. Now for real, X is a vector field. And f is a function. Do we want to say that? Well, I don't need, and let me just say that the infinity of M is functions are valued. Okay, so if you're in this setting, you can just and let me remember that if you have a vector field on M, I'll just do a cartoon because it's quicker. If you have M, you have a point P. You remember that you have X as a vector field, whatever. Right? So the integral curve, let me write it in blue. The integral curve that goes through P, I'm going to call that phi. Right? So phi that goes for X that goes through P is a curve, right? It's the integral curve of the vector field. So I'm going to find the following operation. So imagine that I choose positive epsilon, some real number, some non-zero positive number, and I just define this operation. So take epsilon and X as data. So you have a vector field. So you know how to flow on your manifold, and you take your function f. And this object is going to be a new function, so this whole thing evaluates at a point P, and the value that you take at point P is, you evaluate f at P, okay? You take that value, and then you flow with a vector field for a parameter distance epsilon, right? And so you evaluate f at the point of flow with parameter distance epsilon, which is what I called phi of. So this will be phi of px of epsilon, right? Which is flow that distance, and just take the difference. And of course, you want to normalize by the parameter length, so you're computing some kind of rate of change. So you divide over by epsilon, right? So when you look at that formula, that looks awfully similar to the usual definition of derivative, but there's no limit there, right? I didn't take epsilon to go to zero. I did give it a very evocative name of epsilon, but I did explicitly say this is epsilon, this is not going to zero anytime soon. So interestingly, exercise, if you want, you can take such an operation and just arithmetically compute, and you will find the following. You will find that if you take two functions f and g and you take their product, you encounter precisely this pattern. So you do the first one times the second one, you do the first one times the second one, and you do epsilon times x epsilon f x epsilon g. So that's exactly a weighted derivation that I introduced before. And it's just arithmetic. It's really there's nothing fancy going on. It's just you manipulate your terms, you move around, and you get exactly that formula. So you naturally notice that if you are able to set epsilon to zero, then you get the derivation property, right? And that's what you want to do. Now, obviously, setting epsilon equal to zero you can't do it as a set a value equal to zero, because that's undefined. Right, in your expression doesn't allow you to set epsilon to zero, but you can take a limit to epsilon for epsilon to go to zero. So this is where the limit construction comes into play, right? And so you basically here the sort of conclusion is that in the limit when epsilon goes to 0, delta x of epsilon is actually dx, the usual directional derivative of the vector field x, which is now an element of the derivations of the infinitive m, because in general delta x epsilon is an element of the epsilon there of C infinity of m. Okay, so anyway, that's pretty much what I wanted to say. That I mean, this just to connect back to the entire theme of the program is that this seems to be an example of the discrete case can be encountered in the continuous case by sort of sprinkling a finite set of points that you're going to worry about, but you need some kind of connective tissue between these points. It's not that you sprinkle you literally sprinkle your manifold with points and then you just arbitrarily decide how to move from one to the other. You actually have a vector field, which is an infinite amount of information. Of course, it's a continuous assignment of directions on your manifold that are integrable, right? So they integrate to a flow on your manifold, and you use that flow, you use that data to flow and a small distance epsilon, and you basically just take the difference of your evaluations, right? So anyway, it's I think very evocative the fact that by doing this continuous construction of a finite difference operator on a manifold, you get the weighted Leibniz rule. So you are in the same algebraic territory as in the discrete case. So in a way, this gives probably should give the audience and ourselves some kind of guidance of what is happening here. And perhaps this is a very to some people this could read as this is a strong indication that there is a pattern to be found here. That if I never learned how to take limits, I wouldn't. It's a bit extreme what I'm going to say, but if I didn't know how to take limits, I wouldn't be able to tell the continuous geometry from the discrete geometry in this context on the merits of finite differences, right? So algebraically, that is. So anyway, that's kind of the summary. Sorry, Uti, you have a question.
Yeah, sorry. I mean, I felt like I got a little lost. Essentially, before, like not here,
Yeah.
but before, I still don't get the reason why you get the extra term. Like, what's the reason? Like, if you introduce discreteness, what's the reason you get this multiplication? Like in the discrete setting, what's the physical, like the graph theoretic whatever reason you get that multiplication at the end?
What's the reason why I get? You mean?
Yeah, like why does Leibniz rule?
So it's
Here?
not my understanding is it's not that you get it specifically in the discrete case and not in the continuous case. It's that in the continuous case that the quadratic term vanishes to 0 because it's weighted by this epsilon that you then limit away. So the difference is that in the discrete setting you're not taking the limit that would otherwise make the quadratic term vanish.
But I'm not sure I'm understanding the question. Do you mean why? Because I mean my claim here, this was the finite exposition, right? Like you have a graph, you have some assignment of directed edges x.
No, I get it. Yeah, sorry to interrupt, but like I get it now. Like in the reason why the quadratic term vanishes because you take epsilon to be 0. So there's nothing really that's special going on over here. Yeah, that like my question was that like why do you get this quadratic term? I did not.
The point is that if you refuse to take limits, it doesn't
Yeah.
matter whether you're in a discrete setting or a continuous setting. You like the weight one, like the correct Leibniz rule, so to speak, is the weight one Leibniz rule. The fact that it goes to weight 0 is a byproduct of taking limits. Whether you take those limits in a discrete setting or a continuous one, I think shouldn't matter.
Yes, exactly. Yeah. So the reason is that it's true, right? Like there's no like the. I mean, I because I talked through it. It seems that I argued that it should be the case. I mean, it's just the case algebraically, right? Like you put your definitions and you manipulate, and that's the formula you get, right? There's no mystery there. What I find interesting is that you can define finite difference. you literally don't specify if you don't specify the the nature of the set in which the nature of M, what M is, but you specify, but the data that you require is for every element of M, you need to specify a unique Q, right? So that's a, call that whatever you will. What is that? That's a, yeah, that's a map from that's an endo map, right? Of M to itself. It's an endo, endomorphism, set endomorphism, right? So you just have a set endomorphism as data, right? So with a set endomorphism, you can compute a discrete differential operation. Yeah, like a permutation where you're agnostic about the nature of the set, right? So so if you have that, you already have a definition of a discrete differential operator, right? And the point is that that operator is going to satisfy this Leibniz rule, right? So this weight one Leibniz rule. And the idea is that in the smooth setting, I think the learning points here are crucially that in the continuous setting or the smooth setting, it is sufficient to provide a vector field to get that endo map, right? To get the infinitary permutation, if you like, right? Because it's locally bijective and all that stuff, right? But the idea is that in the continuous setting, you have a structure that allows you to do something like taking the limits to go to zero, in which case you simplify to something that is the usual Leibniz rule, and it has all these algebraic niceties about it. In the continuous, in the discrete setting, you just cannot do that operation, and it's just not defined because obviously there's a minimum step size. But you could take length 2 paths, and that'll be fine. There's no problem with taking an endo map that is defined by the assignment of 2 edges, and that you concatenate them and something like that. Right? There's no problem with that. So, but there is no natural way in which you can say your step distance is going to 0, right? Because there is minimum step distance, and therefore there is a smallest difference operator. And so the smallest difference operator is, in this case, effectively a weight 1 derivation in this general theory. And I have to give some kind of slogan because I just made contact with a collaborator in Australia who is an expert on these algebras, and he's retrieving some literature, and we're going to have follow-up discussions, and he's very willing to come and give a seminar. So maybe in future weeks we might have some guests who are experts on these kinds of algebras for this particular thread of the research. Because again, as a recap of everything I said, the original question is, how are you satisfied that you found the analog of a tangent bundle, or a tangent, or a vector field, or a directional derivative, right? In my opinion, you need to have the entire categorical package of, you have an algebra of functions on your thing, you have derivations on those things, and those things should correspond to something like infinitesimal flows on your thing, and all these correspondences need to be accounted for. And the only thing that was accounted for in the definition of vector field that we had originally in the live stream was that it looks like a vector field. It intuitively makes sense. We draw it, it's like, okay, yeah, arrows, yeah, that makes sense. But this is building towards this more formal construction of identifying from an algebraized perspective. We don't see the difference, like if you're just thinking about finite difference operators, there's no real algebraic way to tell the discrete manifold from the continuous manifold. So this is the kind of things I like to present this in very explicit detail in this stream today, because this is, I think, a good example, a good template for what we are after. I don't think it has to be also algebraic in flavor, but this is kind of the thing that I don't know if Jonathan agrees, but I think this is the kind of thing that is probably interesting to have, something that when you squint and you only think algebraically, you can really tell apart the discrete and the continuous, right? So,
absolutely. No, I think this is great. I have one possibly stupid comment. I don't know, and then one kind of question, one general question.
Okay,
I'm really interested in this how do we how do we go about thinking about this kind of, I guess, what we might call the weighted commutator, right? This arity 2 operation under which the weighted derivations are closed just as the weight 0 derivations are closed under the ordinary commutator.
Mm-hmm.
So Uti brought up this connection to deformation theory. And okay, so I say maybe this is a sensible comment, maybe it's not a sensible comment, I don't know. But so, okay, if we look at sort of deformation theory in the kind of physical context, so, in physics, there's this notion of deformation quantization that's kind of dual to geometric quantization. So, the basic problem is, you've got a Poisson manifold that represents some classical system. How do I construct its quantum mechanical analog? So in geometric quantization, there's this whole procedure by which, you take the symplectic form and you replace it with this pre-quantum circle bundle, and then your Hilbert space is the space of sections of that bundle and so on. But then there's a dual way of doing it, which is more algebraic. So if you like the sort of geometric quantization is like operating in the Schrödinger picture, there's an algebraic version that operates in the Heisenberg picture, where the idea is you start with the you start with your commutative Poisson bracket, and then you construct essentially a kind of almost like a sort of power series of progressively more non-commutative deviations away from that commute. So you equip your manifold with a sequence of sort of progressively more non-commutative sort of algebras, sort of parameterized by what physically you would think of as being like Planck's constant, but in this context we would just call some parameter lambda.
Yeah. And
so lambda is some way of quantifying how non-commutative you are deforming your Poisson algebra to be. Now, the remark I was going to make, and I say I haven't yet worked out whether this makes any sense or whether it's a useful way to think about it, is that we are somehow doing what we're describing here is somehow a kind of post-quantum version of deformation quantization. Because so with deformation quantization, you start from something in which your commutator is 0, and then the role of the deformation procedure is to then build something where the commutator is non-zero. We're now doing something that seems to me like a step beyond, where we're starting from a non-zero commutator, but in an algebraic structure which is closed under the action of that commutator, and we want to construct a new algebraic structure that is kind of arbitrarily non-closed under that, right?
Yeah, I think morally that's what's happening.
So that's interesting. Like when I was trying to, essentially when I was trying to deform Lie algebras, so there's like two ways you could go about it. Either you can start from a commutative algebra, and then you could associative algebra, and then you could define what is, like, you can do the same thing as in deformation quantization. You can define a product, and then you could make sure that the product that you define, if you do a times b, and then you write it as a power series of like a times b in the commutative case plus like something t squared, whatever, and then you do the b times a thing, and then ab minus ba gives you like the new commutator, which is going to be 0 because it's ab minus b and the original one is 0, plus like terms of t and t squared and so on. Or you could go the other way, where you can just assume that you have a Lie algebra at the start. So you start with a Lie bracket, and then you deform the Lie bracket itself. Like I mean, it's just a different structure. So in the star product case, the homology sequence things that you have to obey comes from the fact that you have to obey associativity. Like that's the only constraint that leads to like the existence of star products being into question. You want associativity to be obeyed. In Lie algebras, you want the Jacobi identity to be obeyed. So algebraically speaking, it's just a set of two constraints, and in both of them, you do get like in the Jacobi identity case, you get a sequence that where the deformations are existence of deformations is based on the cohomology groups, and in the product case, the first case, it's just associativity. So I guess both of them, like in your question, I guess both of them, algebraically speaking, are roughly the same thing.
Right. So the only point I'm making is that whatever procedure we need here, it seems to me like it goes beyond standard deformation theory, or at least standard deformation quantization as I understand it, right? Because what typically what you're doing is you're starting from a bracket that is commutative, that where the commutator is 0, and then you're deforming it so the commutator is non-zero, but is still contained in the algebra. What we're
Yes.
doing now is starting from something which is non-commutative in general. So the commutator is non-zero but contained in the algebra, and deforming it into something where the commutator is not contained in the algebra. And then this sort of this putative angle bracket thing that Carlos is describing is is sort of the somehow some projection. So it's like the commutator takes you out of the algebra, but then there's some way of projecting you back into an element that's inside the algebra, and that's kind of that's the role that's being played by this by this new angle bracket. So I don't know, the again, maybe this is just a bad intuition, but kind of my intuitive feeling for what's going on here is we're trying to define some operation that goes beyond, that deforms you beyond ordinary deformation theory, so to speak.
Yeah, I mean, I don't have a strong intuition for usual deformation theory, but what I know for sure is that it is very likely that we're gonna have to do something that is, I don't know, I don't know if it's beyond, but it's certainly distinct in some sense, because what I wrote in the screen here is that I think it's very likely that you would consider the set of all weighted derivations, not the lambda weighted derivations, which is the usual thing that people do in the literature, which or like your formal parameter like h bar, and you're doing your formal extension with a fixed parameter h bar. I think that what seems to me more I don't know, sensible and more parsimonious is that you, in some sense, the limit point of all the difference, the finite difference operators were this sort of weight zero derivations algebraically. So they correspond to a single point in a continuum or a set of possible derivations, right? But in a way, those when you don't want to assume that you are at that point, you can just simply say, well, these are all my derivations, right? Like I can be in any of them. So to me, the compositional structure, it will be very unlikely, I think, to think that lambda derivations compose to be lambda derivations, right? And so it might be that one derivation that is lambda weighted, the other is mu weighted, compose to something that is lambda mu weighted or lambda plus mu weighted or whatever, right? So some kind of dependence on the weighting as well. So in general, what I want to say here is that you might want to consider this larger set of all the weighted ones, which indeed correspond to all the possible ways of defining finite difference operators in some geometric setting, discrete or otherwise, and then in there, it might be possible that you have this bracket, because indeed you will have the commutator bracket as a subalgebra. This is obvious by construction, so what I mean by this is not really deformation theory is that there is no single parameter. This is, and in fact, it's not even a parameter. It's a ring element. I mean, it's not. Not all rings look like they are a knob that you can turn, and it feels like a parameter that you're turning to zero, right? So, so it's certainly something more general than that. That's what I meant. And again, I wish I had time to work on this, but I've known this for less than 24 hours. I was doing all kinds of checkings and trying hard to prove that this is additive, but it's not.
It feels almost Grossman-like in some way, right? Like, so if you can define a wedge product over scalars, right? You can define a wedge product over zero blades, but it's kind of trivial, right? Because it's your field of scalars is kind of trivially closed under that wedge product. But as soon as you go to one blades, then you take the wedge product of that, and you're no longer in the space of one blade, you're in the space of two blades, and so on.
That's a good analogy. Yeah.
And so as soon as you go to non-zero K in your K blades, then you have to consider not just a single space or a single field. You have to consider this whole infinite tower of higher vector spaces. And it feels, I mean, from what you were just describing, Carlos, it feels like something similar might be happening here. So that would be kind of cool to investigate.
Yeah, something like that.
Sorry,
yeah.
And Oti, just before you jump, I did want to ask pose one thing, which is, so, you mentioned that there's a bunch of this nice algebraic structure that holds in the weight zero case that fails for any non-zero weight, among which the this non-closure under the commutator is a kind of is a sort of standard example. But you also mentioned that you get this R module structure that breaks as soon as that doesn't really hold as soon as you go to non-zero weight.
Yeah.
Could we expect just as we can think of the potentially as being this kind of this angle bracket thing that is like the kind of weighted commutator? Can we imagine there being a kind of weighted analog of left and right R modules that which is the sort of the algebraic structure that is preserved even in the non-zero weight case, or is that completely hopeless?
No, I think that's very likely. I mean, oops, my tablet turned off. Give me a sec. Yeah. So I think that's very likely. Let me just illustrate this very briefly with an example. So where do I have this? Oh no, it was up here. Yeah. So these are what this satisfies and this fails, right? So what do I want to say? Yeah. So it's very easy to show that if you have a derivation D of a ring, then for R, an element of the ring, that, I mean, this is what I wrote there. I don't have to write it again, right? So it's very easy to see this, right? That's a, you multiply by a ring element, the ring element stays in its position, and you just and you recover that. But in this case, there's actually, let me talk about the sum, because the product might need to actually be an R algebra, but the sum is actually, I'm going to show a different whiteboard because I have that computation. Is that? Yeah, I have it here. Oops, is that right? Yeah. So if you try, oh, I was calling them quasi-derivation at this point, but same thing. So imagine that you have to weight one derivations, delta and del, and you define the sigma as the sum of delta and del, right? So you want to compare, you want to know whether sigma is a derivation of weight one, right? So you want to know to what extent sigma satisfies the rule AB plus delta delta and so on. So here's what happens. It's not terrible, but it's a clear departure from additivity. I mean, the first terms are or additivity, so this will be, checks out. But then you get into the cross terms, and you get this, which it's the extra part that is not there. So this just illustrates that we are not hopeless, because it's not just that there's no way that this can happen, but there seems to be some compositional structure that is kind of modifying things in the background. And by the way, I think if I remember correctly, when you do this computation, yeah, I think the weights are multiplied there, right? Is that right? Yeah, because you get multiplied or even squared. I don't know, but anyway, so those terms carry the weights in, because they are non-one weights. They are going to appear if your ring is commutative. Let's say they're going to appear in the as operations, right? In the weights are going to operate in those terms. So yeah, I think there is some room for exploration. That's why I spent like the last few days sort of before I discovered the fact that these are weighted algebras and there's literature that I can read. I mean, this was before I did. These notes were from before I knew that these things were known. So yeah, I was very glad to find that this some theory about these things is known. But again, I would say also for the audience, it's always the bittersweet feeling of research. So on the one hand, it is a bit sad that this fails to satisfy the easy known property. But on the other hand, if it did, it would be a very well-known structure already, and there would be almost nothing new to find there, and therefore nothing for us to research about and to discover. So I think this has the signature of something that might be worth our time, because it doesn't feel like it's completely offshooting to completely untractable terms or something like that. It feels like, it has some change but I think the potential gain outweighs the inconvenience of all this lack of algebraic behavior, because the potential is it's going to be a language that unifies in a particular narrow context of difference operators of these particular constructions, but it unifies algebraically the discrete and the continuous setting quite uniformly, right? So it can be a very toy model of the entire program that we want to do, right? So and that's because I have more familiarity with Lie algebras and so on. That's why I was suggesting to look microscope look into this particular aspect of the constructions, because I was suspicious that this kind of phenomenon might happen. If you remember in the first, if the audience was around in the first live stream, I was saying, oh, it will be amazing if there is a Lie algebra, and it was all very hypothetical and sort of very open-ended. By the end of the live stream, there was a very strong hint that we prematurely, or I prematurely announced that it was actually a Lie algebra, and it was technically true if the weight was 0, but the weight is not always 0, and so yeah, I think I've been vindicated in the sort of intuition that there was something that looked like it could be Lie algebraic or Lie algebra in flavor, so to speak, or Leibniz in flavor, and that would be indistinguishable between the continuous and discrete. And so that's why I think it's worth exploring at least a little bit this weighted derivations, and to maybe have a seminar with this guy that knows about them, and sort of explore a little bit. And I mean, not to detour too much, because this gets really could get there might be academic mathematicians just for years just writing papers on weighted derivations, and honestly I don't have it in me to do anything like that, and I don't think that's the role of the institute, and I don't think we need to do that. But I think it's a good testing ground for our kind of approach, and again, if we are successful at identifying examples of these kinds of algebras coming from graphic structures, coming from how you endow a set of vertices with something like a connection, or something like a metric, or something like tangent bundle and things like that, I think we can make a relatively nice splash into the whatever communities that might be interested in this sort of structures, right? So anyway, it feels good to say, a couple of weeks later, there's already kind of a realistic bit of an example that might sort of illustrate the scope of the entire project, as well as the project being scoped as a whole. It's certainly good feeling.
Yeah, and as Carlos mentioned, I mean, it's generally a good kind of heuristic for interesting research directions, that there's it's not totally trivial. We don't just reduce to kind of standard calculus because the Leibniz rule holds, but it's clear that there is some structure here, right? It's not just completely wild and whatever, right? So which is normally when you have that combination, that it doesn't reduce to something that's very well known, but it's structured enough that you can see there's an inroads. That's normally that's a good indication that you should go explore that particular thing.
Exactly. Yeah. So hopefully Uti would be sort of a fellow sailor in the unruly waters of this kind of unknown or partially known structures.
I mean, I do have a question.
Yeah, please go ahead.
Essentially, I mean, this is good. This is a very stupid question, but assume that the classification of all lambda derivations where lambda is a ring, and then you're taking essentially anywhere it's any ring and stuff, because I mean, I don't know, standard deformation theory is only for when it's like T. it's very basic. I mean, how is that going to be, how are we going to use that? I see to the future. How are we going to use that?
Yeah, no, that's a very good question. So if I understand correctly, you're saying assume that we know what these algebras are, and we have a classification, even a complete classification of these algebras, which is, I think, is completely hopeless in practice. But let's imagine in the best case scenario, I think it's a very good question to pose it that way, that we have something like a classification. Well, I would say the way I would use that is I would look at the algebras that you get from continuous smooth manifolds and say, choose your favorite class of manifolds. Maybe you want to look at Riemann surfaces, or maybe you want to look at whatever, three-dimensional and non-orientable manifolds, whatever. Choose your favorite class of manifolds and basically see what such algebras, unknown algebras, would appear in those, and then look at the discrete cases ones and try to see what you gain or what you lose, whether you can capture continuous in the finite, in the discrete, right? Like, to me, one of my hypotheses, and again, this might sound too strong, but I have the feeling that because of this argument that mathematics is all finitary and we're actually always computing in a finitary regime, I have the suspicion that it might be possible to formally prove that what the infinitary continuous machinery affords you is actually recoverable with a finite discrete setup. I think that, to a lot of people that would sound very strong, but I have a feeling that this might be possible, or at least for some regime or under some conditions this might be possible. And and to some degree the simplicial geometry story, the simplicial discrete differential geometry is almost a testament to that, the fact that you can compute exact cohomology, or exact cohomology features of manifolds with the triangulations, right? Like you don't have to assume an embedding and then use the fact that you're embedding R3 to use a vector calculus computation to get those numbers. Right? You can triangulate, and those numbers are going to fit, right? So Jonathan and I had a moment in live stream last week where we said, oh, of course, so we could, or at least I realized that it was very clear that we could map continuous manifolds to discrete manifolds in this way, where you embed the discrete manifolds and you weight your elements, your edges, and so on with data that is extracted from the smooth manifold. So when that's the case, you're in any realistic setting, right? In any physical model, for example, you're always, in any case, you're anyway only going to look at a finite many points of space-time, right? Like you're never gonna sample infinitely many points in space-time. So if you have a continuous model that has infinitary objects in it, it might be enough that you make a discrete reduction, like the ones that we've talked, like Jonathan has shown many times before, where you basically sprinkle or you choose some collection of particular points, and you infuse the data from the continuous model into the discrete model, and then the discrete model carries finite amount of information, which is anyway the amount of information that you were going to be using in an experimental test, for example, or making numerical predictions about some model or something like that, right? So to me, that's why I'm arguing in this direction, that there might be a formal argument, where you can say, well, in general, I can always package the information of a continuous theory into a finitary discrete theory, right? So anyway, that to me would be one of the main tools to justify that formal claim more generally.
It's almost like a kind of theory of lossless compression, but for geometry, right? Like, so information theory, the whole concept of Shannon information, etc., in some sense was really born out of people caring a lot about, under what situations can you do perfectly lossless compression? If you allow for lossy compression, but with certain bounds on the loss, what isn't achievable. And what Carlos is kind of saying is, in some sense, that or I guess one way to reformulate it would be to say, there's obviously in a continuum geometry, there's an infinite amount of information, but you may only care about some of it, or there may only be some aspects of it that are observationally accessible, and so it's perfectly reasonable to ask in exactly the same way: can we construct a lossless compression of that continuum geometry into a finite set of into a countable set of data? I mean, this relates to long-running philosophical questions in relation to the physics project and other things, like when people ask, is space-time discrete or is it continuous? In some sense, it kind of doesn't. You might say it doesn't really matter, because it's like, even if it's continuous, when we build our experiments, we only have access to sort of finite degrees of freedom. The observables we have are may still be kind of discrete observables, and so at some level, it's an almost theological question whether you believe that the underlying data structure is discrete or continuous. The only parts of it you can access behave like it was discrete. Same with computability, right? People ask, do you think the universe is really computable or is it non-computable? At some level, it doesn't matter, because if the only experiments you can perform have computable values of the observables, it's like the universe behaves as though it's computable, irrespective of whether the underlying data structure is or is not. Okay, Uti is saying that he needs to go and find a power outlet. Did you find one or?
Oh no, I think should I leave for like 2 minutes to find one?
I don't know. Okay, so maybe we should take a moment to figure out what we're going to do. So we've been going for nearly 2 hours.
Yeah.
We could, depending on how you guys. Okay, so question is, what do we want to do now? Is there if we assume we probably don't want to stream for more than maybe 2.5 hours or so.
Yeah.
Is there anything that we think is worth doing in the time we have remaining, or I mean?
Yeah. Well, I didn't have anything particularly in mind, because, as I said, I had a kind of a plan 2 days ago, and then I discovered this entire set of literature on weighted derivations and had meetings, following up and so on. So we could. I wonder what's good use of this time. I don't know because we're gonna meet in private with Uti to decide a few things anyway. But I wonder if there is. I would appreciate having a more of a higher level conversation about this question that I had in my notes, the fact that what is usually different ingredients in the continuous setting seems to be collapsed onto just graphic data and in a very degenerate way. And perhaps more specifically, I would be interested in knowing your thoughts on what is the actual difference between. So far we've given a few constructions of analogs, especially tangential related analogs like vector fields, tangent spaces, tangent bundle connections, etc. So far, all I've seen has been subsets of a directed graph, or different directed graphs built on the same set of vertices.
Right.
Do you agree with this? Have you seen? Because yeah, sure, the vector field is an assignment and all you want, but that is a subgraph or one graph assumed to be sort of like labeled in a certain way. Similarly with connection, similarly with tangent bundle and so on. So could it be that all those notions are somehow muddled up, not in a bad way, but they're muddled up in the entire framework of directed graphs, and it's a matter of properties of directed graphs that is going to discern whether it's, that should be your vector field, that should be your tangent bundle, that should be your connection?
Yeah, I that's an interesting question. And that's kind of, I guess intuitively that's more or less what I was expecting. That's we would find ultimately it all just comes down, you build this directed graph structure that is one's connection, and most or all of the standard apparatus that one cares about is really expressible in terms of subgraphs of that directed graph. Yeah, it's an interesting point that you make. I know we remarked on this in the very first live stream we did. The fact that in the continuum setting there are these very clear distinctions between topological space, smooth manifold, metric space, measure space, etc. Yep. Just sort of canonically, if you just take a graph It's like it's very hard to say. It's very hard to kind of to make a graph that is a topological space but isn't a metric space. Like you can do that by taking transitive closures and doing other things, but it's still somehow very unnatural. That yeah, you're right that there is something. It seems to be there is something about discrete geometry, or certainly about graph theory, that collapses a bunch of these notions that are traditionally distinct, into common things, and that may be a byproduct of something as simple as there are only so many ways that you could take subgraphs of a directed graph, right? I don't know. Yeah, it'd be interesting to figure out at a higher level why that happens. I'm not sure I immediately have anything especially profound I can say about that.
Yeah. No, I was just probing on intuitions and thoughts. I know that this is going to be more sort of like hand wavy, but my intuition at the moment is that when you go to the infinitary case, the continuous case, because I mean, you might have this, this perspective that you begin finite and you sort of build up and you go to some kind of statistical limit, right?
Right.
So if you take that perspective or that metaphor almost in a way, you could imagine that because a manifold is an infinitary space, but it's very finitary in some sense, right? In like for example, you have your chart, your local maps to your local charts to model space, and the model space has something finite about it in terms of dimension, for example. Right, and of course you can do infinite dimensional manifolds, but then the finitary aspect appears more as a way of closing a diagram and blah, blah, blah. I mean, anyway, the point is, it might be that when you go to the infinitary case, the fact that you have to tame the growth of your size, the size of your set, right? Like how your set is. So you basically have to contain the beast of infinity, right? Like you need to, it needs to have the cardinality of R basically, and not more, than in some sense, right? I think that might be what the price you pay is like. Okay, so now what in the discrete case was, a more unified structure that just had details about it, that are more sort of combinatorial details about it, that you could track and interpret as something that can be put in the continuous case. In the continuous case, that is actually more information that you have to supply, right? Because that's the way I intuitively think of these things. It's like, it's kind of a market of information. Like these structures, you have to, you get a manifold, you have to pay for a metric. You don't have a metric for free, and this kind of logic, right? In the graph, you give me a graph, you don't have to pay. In a sense, it's like, you have a set of points, you have to pay for a graph that doesn't come for free. But once you buy a graph, it comes in a bundle, and there's like an offer in the supermarket that says you also have a topological structure, you also have metric structure, you have measure, you have all this stuff, right? So it's kind of that thing in geometry. There's phenomena like that. When you buy a metric, you also get a connection for free. You get the Leibniz connection for free. There's this phenomena. It just might be that when you go to the continuous case, the smooth structure just disrupts that kind of like bundles in the supermarket, and it's like, yeah, we don't. You have to buy. You have to tame the infinitary. The cost of taming infinitary sizes and so on is like you need to specify more information for the otherwise well-defined notions, right?
Right. And I think that's a very nice analogy, and I would be tempted to conjecture that to go one step further with the conjecture, which is that I suspect that the reason why it's almost like some kind of symmetry breaking thing, right? When you go to the continuous, there's at the discrete level you have some very strong symmetry where topological spaces, metric spaces, measure spaces are somehow all the same thing, and then as you go to the continuum limit, that symmetry gets broken and they end up being distinct. My feeling for why that happens, or my conjecture for why that happens would be that it's ultimately to do with commutation of limits. It's to do with the fact that when you say we take a continuum limit, it's almost never that there's one limit you're taking, right? So okay, to give a very concrete example that hopefully motivates that conjecture. So suppose you have a graph and we're doing our tangent space definition. So we define the kind of infinitesimal tangent space at some point as being all paths of length n or whatever, right? Emanating from that point. So if we now take a continuum limit of that, then we're really taking at least two limits. We're taking the limit as the size of the graph goes to infinity, but we're also taking the limit as that n goes to infinity. The extent of our tangent vectors also goes to infinity. But crucially, the length of the tangent vectors should go to infinity less quickly than the size of the graph. If we want to reconstruct our standard geometrical intuition for a tangent space. If that doesn't happen, in other words, if we end up in the limit with sort of infinite length paths that are comparable to, that are the sort of the same size as the infinite sized graph, then we're going to end up with a situation where there is no fine-grained information anymore. All you have is kind of very broad connectivity data, but you can't really, but essentially all of your graph is kind of just consists of a bunch of completely connected components. And so in that case, what you end up with is something that's much more like a topological space and not at all like a metric space. Whereas if you tamed the limit of your path, if you tamed your path length limit so that it went to infinity more slowly than the graph limit went to infinity, then you wouldn't have that same problem. Then you would preserve the metric structure. So my suspicion is that the reason why you get these distinctions in the continuum case is just that the distinction between what is a topological space versus what is a metric space, or what is a metric space versus what is a measure space. Those are distinctions that occur because you take some, because certain pairs of these limits just don't happen to commute, and so in particular, if one of those limits, if you take one limit to infinity faster than you take another limit to infinity, certain things that would have been the same end up getting separated.
Yeah, I mean, I'm developing intuition as we speak. I mean, it's something that is kind of alien to me. How to think of
right. I mean, I can make it even more. I can make that even more concrete by saying, like, if we imagine, we do this discretization, the standard discretization procedure where we just connect, we randomly sample points, we connect them if they're within a certain continuum distance of each other. So one limit we can take is just the number of sample points goes to infinity. Another limit we can take is that the connectivity goes to infinity, right? And so to get the continuum, both of those limits have to be taken. The out degree of any vertex has to go to infinity, as well as the number of vertices going to infinity. But if we take the out degree to infinity too quickly, then we end up with a situation where the graphs are just complete, all of our graphs are complete graphs. And so that tells us about the topology of the space.
Right.
But we somehow lose all the information about the metric structure of the space. My suspicion is that there are a bunch of cases where you can do that, where there are a bunch of these kind of hazards, where if you take the limit slightly wrong, then you end up separating two concepts that in the discrete case otherwise would have been unified. And so you break your, as Carlos was putting it, these nice sales packages or whatever that you would have got for free in the discrete case. Suddenly you don't get for free anymore if you're too blasé about how you take your limits.
Yeah.
I mean, I'm curious. Are there any other objects except for graphs? Because I only have an intuition for graphs based on just this discussion. Is there, what are the other discrete objects when you take it to the limit in some intuitive definition, some intuitive visualization, like Jonathan just told us? That is the same thing.
Simplicial complexes would be the other obvious case. I mean, those are not really distinct because they're kind of trivially interconverted. Like, you can, for any simplicial complex, it has a kind of dual, which is a connectivity graph, and vice versa. But yeah, I mean, so when you do a simplicial decomposition of some topological space, then there is a limiting operation related to the Minerva recovering and those things that allows you to kind of reconstruct the continuum space from that in a way that is, as I say, related to, but I would say somewhat distinct from the kind of graph-based discretization. There may be others. I'm not. Carlos, do you have?
I mean,
comments?
I don't have more examples of that specifically, but I understood the question slightly differently. Do you mean?
Oh, sure.
Do you mean perhaps that, we are saying if we provide an undirected graph on these vertices, that's going to look like a metric angle topology and so on, or directed edges would look like vector fields or tangent vector and so on. you mean what other graphic or hypergraph-like things will translate into geometry, or was it something else?
No, I mean, I guess it's what Jonathan said.
Okay.
I mean, currently we only have intuition, and we're claiming things about how, these things collapse, and you collapse like the notion of if you like expand the connectivity, if you make it a complete graph, then the distances should be one, and so it's kind of hard to define everything together in a discrete case. Like I was just asking for more examples. Like I was wondering whether this is just an artifact of graphs or something that's really philosophical. Like,
No, I think it's deeper than just graphs. I mean, so like if we take another example of discretization that you could consider, so when you define a CW complex, right? So what you've got, you take some topological space, you kind of decompose it into a collection of these open balls, related by this gluing map. And so each one of those open balls is then a cell in that CW complex, and if you just consider the collection of cells, that's purely combinatorial data. If you want to reconstruct the topology of the original manifold, one way you can do that is you can just you can take the number of these open balls to infinity somehow. And then all of the topological, and then there are theorems that effectively tell you that for spaces that satisfy certain separability axioms, the gluing maps, or the properties of the gluing maps between those open balls in that limit completely determines the topology of the space. And in fact, somehow large swathes of Morse theory and so on are sort of predicated on the fact that you can reconstruct everything there is to know about the topological space from the analytical properties of those gluing maps in that limit. But there again, you have the same issue, right? That if you imagine taking a CW complex now, not of a topological space but of a metric space, then you have to there are now two limits you have to take. One as the number of balls goes to infinity, the number of cells goes to infinity, and the other as the radius of each ball goes to zero. And again, if you fail to take those limits with appropriate commutation properties, if you take one of them, if the size of the cells goes to zero too fast relative to the number of cells, you're going to miss certain topological features of the space. And so I think it's exactly the same. My suspicion would be that any reasonable discretization scheme you came up with would suffer from an analogous problem. It doesn't matter whether the data structure is graphs or whether it's CW complexes or whether it's simplicial decompositions or doesn't matter whether you're splitting your space into triangles or pentachora or whatever, right? I think you're going to end up having effectively the same problem.
Yeah. So one final comment I would like to throw in before we do some wrap-up conclusions or something. What about, so I don't think we should dismiss, because, okay, before I collect my train of thoughts. So, yes, this notion of taking limits in different orders and like the commuting properties of taking these limits and so on, it's important. I think what I see in smooth differential geometry and conventional sort of geometry that works for mathematical physics is that it's not only that you end up with a theory that that has a nice algebraic formulation and it makes sense and so on, but it's that you end up with infinitary sets that have several regimes that are very, very finitary, right? Like you for example, you don't have manifolds that it's difficult to have. For example, if you start to count homology, right, and you look at the fundamental group, right, I'm gonna make an example. It might be technically incorrect, but I think you will get the point across. It's okay to have manifolds that have countably many holes in them, right? You have you have a countably many copies of set in your homology groups and so on. But it will be very hard to imagine a smooth manifold that still fits the definition of smooth manifold that has uncountably many copies of set, right? Like that probably will violate the smoothness condition in some regime because of the nature of what a homology group is, right? So what I'm trying to get at with this particular example is that we should not dismiss the fact that it is very likely that if we begin with this infrageometry perspective, and I think that this name is very justified for what I'm going to say, if you begin with infrageometry as a general perspective, we should be expecting to get all the not so nice geometries that happen sort of in between smooth geometries, right? Because I mean, smooth geometries are, they are kind of infinitary, but as finitary as you can be by being infinitary in some sense, right? Because you have like constant dimension, finite constant dimension kinds of things. Like you have this all these local theorems about local integrability. You have all these like niceties of, and sure you can put sort of like finite differentiability instead of infinite differentiability, but still things revolve around those kinds of limits. So I think we should be expecting, because I have experience with C-infinity geometry where you're doing everything over smooth, because there's good reason to do that. But we are gonna have we should in principle be covering all the subtleties of finitely differentiable spaces, of continuous spaces, of fractal spaces that are no longer continuous or are continuous but nowhere differentiable, and things like that. All this kind of all the zoology of spaces that are usually excluded from geometry as a discipline, right? I think we're gonna be recovering in some way, right? Like, or at least we want to be claiming that we are gonna say something meaningful that might apply to those spaces. So I'm making this mostly as a general comment. I don't think this really changes anything of our approach or offers anything new, but it might be worth keeping in mind that at some point it could be interesting as an exercise to sort of like flex the abstraction muscle, to try and, for example, look at literature of fractional geometry or something like that, geometry in fractional dimension or things like that, right? Where if there's a good notion of derivation on fractal manifolds, things like that, then it might be an interesting, the pattern should be there, like we should recover that exactly the same way we recovered the smooth one, right?
Absolutely. I mean, in some sense, I'd say this is both the blessing and the curse of being constructivist, right? It's right. Like, so with traditional axiomatic mathematics, you define your axioms in a way that it sort of excludes all the stuff that you consider somehow to be pathological. You focus only on the cases that align well with your intuitions and so on. But when you go, that's a very top-down way of doing mathematics. What we're trying to do is kind of bottom-up, very constructivist, and somehow suddenly you find yourself being exposed to all of these random pathological examples that you somehow swept under the rug with your axiomatization. And so yeah, absolutely. You see this, for instance, with graph rewriting, right? That, so we know that there are rewrite rules that produce manifold-like graphs, but they're very, very rare. And so, the vast majority of rewrite rules produce crazy, fractal-like or highly complex or nested or, graphs, and even the ones that produce kind of what appear to be plausible manifold-like results, they often end up being weird orbifolds because they have sort of singularities properties, or that, there are places where the dimension kind of appears to smoothly vary in ways that manifold, shouldn't happen with a manifold, and things like that. So suddenly, you discover there's a much richer zoology, a much richer taxonomy of these structures than would have been evident if you only looked at the axiomatic description. And yeah, absolutely, I completely agree with your intuition that, and it's a nice way of thinking. Again, it's a nice way of thinking about, I guess, really what certainly algebraic topology is all about, has been taking, continuous structures, but finding ways to describe them using only, finitary combinatorial data.
Exactly.
And in that sense, I guess it's a kind of, one could think of algebraic topology as being a kind of a microcosm of Carlos's, view of the philosophy of mathematics. That it's really all about taking some infinitary structure and finding some finitary representation of it that still preserves all of the interesting stuff that you actually care about, which is precisely what homology theory, cohomology theory, etc. are somehow all about. Yeah, it's an interesting question. I like the idea of, in addition to looking at the pure bottom-up problem, I like the idea of saying because I don't know. I genuinely don't know whether there is literature on this. Maybe you do. I like, what happens if we take, what happens in the limit of, say, arbitrarily large homotopy groups. So you have a manifold with a certain number of holes. What happens if we take the limit as the number of holes goes to infinity? What does that break and how? Surely someone's looked at that, but maybe not in that much detail. And so and that's another way, as you say, that we may be able to kind of build intuition for the kinds of, because one obvious thing is we need to figure out what kinds of pathology should we look for, right? What kinds of pathological cases should we expect? And asking those kind of degeneracy questions is one way that we might be able to start indexing the sorts of pathologies that one might reasonably expect. That's an interesting point.
Yeah, no, definitely.
I like that.
Yeah.
Yes, and I mean, what one interesting kind of from a more mathematical viewpoint, one thing is that one thing that'd be super cool as a sort of stretch goal of this whole program would be if we can start to make essentially more or less precise measure theoretic statements about how common certain objects are, right? So it's like right now, just as we can okay. To make an analogy, so with the advent of computability theory, all of a sudden we started being able to make fairly precise statements about this is how, in a kind of measure theoretic way, this is how relatively common computable numbers are versus non-computable ones, algebraic numbers versus non-algebraic, transcendental versus non-transcendental, etc. What would be super cool, because I'm pretty sure that there's no systematic procedure to do this right now, and infrageometry, if we could develop it, would be the first such procedure, would be the first formalism which such questions could even be made well posed, would be if we could start to say, if we just kind of enumerate, if we just systematically enumerate spatial structures or space-like structures, what proportion of them are metric spaces, what proportion of them are smooth manifolds, what proportion of them are orbifolds, if we and so how much of that space is taken up with pathological cases of various kinds? That would be a super interesting, if we can actually get kind of more or less quantitative results about that, I think that would be a super cool kind of metamathematical implication of this this whole program. It may be that that's just ultimately too intractable, but I think it's a nice thing to bear in mind as something we might potentially be able to investigate.
Yeah, indeed. Completely agree on that. Should we make some final remarks, some summary, or maybe set out some objectives for next time? Although we're gonna meet probably before we live stream.
Yeah, so I think so. So I think as Carlos mentioned, I think we may have a there's no, I mean, not that we're discussing anything particularly sensitive, but I think just so as we mentioned at the start, so Uti has just been onboarded as a new fellow. We need to kind of nail down in a little bit more detail precisely what kind of projects he's going to be working on. So what we'll probably do is we'll have a private meeting, and then what I think would be really nice is either, I don't know, I mean, maybe as part of next week's Infrageometry stream, or maybe as a separate stream, to sort of introduce to the live stream audience, precisely what it is that Uti will be working on. So I don't know whether you guys want to do that as part of next week's regular stream, or whether we want to have a separate stream for that. What do you think?
I mean, I think it largely depends on the project I end up doing. If it's more on the geometry side of things, like what we discussed today, then definitely I'll be in the live stream next time. But if it's more like pure causality side of things, then I don't know, maybe we need a separate live stream or something, or we could discuss intersecting ideas in the upcoming live stream, something like that.
Fair enough. Okay, so in terms of right, so maybe the way we should do this sort of as a negotiation is if we each state very selfishly what they want to get out of the next installment of this. So what I'm really excited to get to is, now that Carlos has kind of unearthed this whole world of weighted derivations that I at least need to try and understand in more detail, certain questions become kind of immediately start to pose themselves, right? So, in standard differential geometry, when we impose, torsion freedom, that's really, amongst other things, that's a way of saying that the Lie bracket of vector fields vanishes. And so there is presumably an analog of that for weighted derivations as well, where whatever this weighted commutator turns out to be, we can also say, maybe there's an analog of the Levi-Civita connection where that weighted commutator vanishes. So because what I really want to start to get to is, going back to the stuff we started thinking about in relation to directional derivatives, covariant derivatives, metric compatibility, etc., and seeing if we can formulate that. We were doing that before using this very naive kind of finite difference approach. We now know that there's a more sophisticated sort of existing literature tree on these finite difference, weighted derivations. What I would really like to be able to get to is for us to start systematically exploring how would a covariant derivative work in if you're in a ring with whose derivations are have non-zero weight or something. And possibly in parallel, I would like to then go back to figuring out exactly what are the analogs of, if we take our favorite, I think we more or less know how the metric works, the metric tensor field, but going back to our kind of favorite weighted, our favorite continuous tensor fields, this angle tensor we defined before, or basic curvature tensors and things. I would really like to go and see if we can start, now that we're starting to build up this formalism, see if we can kind of derive those things from first principles too. So that that's what I would ideally like to be doing in the coming couple of streams. Carlos, what would your objectives be?
Yeah, actually, I would say it's almost a subset of those objectives, and perhaps, specialized to the context of these derivations. I think it's a good opportunity to really exhaust what these things offer, at least the known theory about the weighted derivations, because, as you said, it will be really interesting to be able to just do the analogs and do the finite difference analogs of all these constructions and see how you can talk about commuting vector fields and torsion, connection to torsion and things like that. And I think it will be a very nice sort of tandem development tempo between, on the one hand, you have the finitary graphic structures to go on, and you're like, okay, I have these ingredients, what do I cook up with them? And on the other hand, you have sort of more traditional formal algebraic theory informing you, okay, you should be, by studying these weighted derivations on their own, you have sort of a guidance a guideline of what you should be looking for, right? And obviously we also have the expectation of what smooth geometry looks like, but we've already seen that we probably have to content ourselves with finite difference operators in the smooth context as a real reference for what is happening in the discrete case. So I would say I would particularly focus on and I'll be able to, and I wish to get out and be able to report on progress on the one hand, just weighted derivations, knowing what they can afford and answering some fundamental questions like about whether this is known or not the actual answers, mathematical answers. Knowing them will be great, but knowing if they are answered, and if so, what the answer is, for questions of like, do weighted derivations carry an algebra structure, this angled bracket that we discussed earlier, are those is that bracket how does that bracket relate to Lie algebras, which we already know it has to contain them in some algebra in some sense, but how do those brackets relate to integration properties of this thing? So what would be the group-like structures that integrate this Lie algebra-like structures and things like that? Is there a Lie functor-like construction for these things and so on? Anyway, the usual sort of gymnastics of differential geometry questions that you have for those structures. So that I want to be sort of, I will meet with this colleague of mine a couple of times, and we'll review the literature, see what's there. and we try to think of something if we don't find any results in the literature. And on the other hand, I would be interested in just seeing what can be done with the graphic data, and seeing what is natural, because I think that last time in the last two streams we got into very nice pockets of sort of like mathematical creation, where we were both saying, okay, yeah, we have this data, we have this this philosophy that if it's not there for free, I cannot use it, and if it's there for free, then I need to check whether I have more choices and whether there's dependence on the choices and things like that, and to do that for the most basic constructions in differential geometry, like we were saying, like tangent bundles and tangent vectors and vector fields and things like that. It's like what mostly like especially a connection. I think what I want to really get a hold on is the entire tangent machinery of a manifold, which currently I'm mostly thinking, your connected manifold, your sort of basal space is going to be some undirected graph, and your tangent infrastructure is going to be the directed graph induced by it. And it might well be that the undirected graphic structure might not even be pairwise necessarily. You might have some higher order hypergraph that is undirected, but the directed graph structure does involve just pairwise, because these, as you all know, undirected directed edges are nothing but unions of pairwise directed edges, right? And so I think that I wouldn't be very confident in claiming that undirected graphs are in some sense the end of the story about metrics and measure and so on, but I will be much more confident to try to claim something like directed graphs are kind of the tangent machinery of a manifold. I think that I will be much more comfortable with stating, and so I want to understand that. So we've never mentioned this in our conversations because I don't think it was really relevant, but something that is clear that you have in any finite directed graph is the groupoid of paths, right? So this is the analog of the fundamental group or the fundamental groupoid of a space. So anyway, I want to understand, and I think that has all the information, all this story about tangent vectors, tangent bundle connection, to what degree a vector field is just a distribution of things or is just a subset of a larger thing itself, and so on. It's like I want to understand that well, because I feel like if we get that right, and we can match a formal definition in the existing theory of weighted derivations, and we can make some nice argument about these are the things and how they work and so on, I would feel very confident that there's a serious pattern to unveil at large in the but it's mostly the way I would summarize this is that this is me getting the sort of biting on the juicy part of the potential correspondence. Like I think you've already charted by the constructions that you've done before with the more statistical sort of like your work on gravitas and all this, your experience with doing GR in this generative way with hypergraphs and so on. I think you have a lot of sort of mileage of seeing differential geometry come up and emerge from the discreteness. I feel like I need my fixture of that sort of input, and I think that will come by really figuring out the tangent structure of finite sets, which is like it's weird to say, but I think it's provocative enough to be entertaining.
Yeah, absolutely. And you're right. I think that sounds pretty consonant. So I think that's a good. We have a fairly clear path for the next stream if that's the direction we want to go in. I don't know, Uti, do you have are there particular topics that you think we should aim to hit in the next week or so?
No, I mean, I think you covered a lot of it, which I've never thought about. But essentially, like for me, yeah, I have. I mean, potentially there's 1,000 things I could explore. 1,000 things. I have a lot of questions. So like one of the things that I'm probably interested in as like baby steps is that I mean, so we talked about how certain like finitary constructs, discrete constructs, algebraic constructs are the only things that might matter, and then the extra continuity might actually be may just impose more constraints. And so what I will probably try to do is, I don't know, I want to try to like maybe someone has done a systematic study of like minimalistic differential geometry or something, or like what are the actual things in differential geometry that are important. So we talked about how simplicial geometry, where you break the manifold up into triangles, can reveal like a lot of the information, and you don't need the actual topology on the manifold to do a lot of things. I feel like for our formalism, we start with definitions of tangent spaces and um, and yeah, essentially like a lot of tangent spaces, connections, metrics, because that's like the most obvious thing to do. I'm also kind of more interested in the category side of things. I mean, I'm sure a lot of it has been figured out, but I just want to delve more into like the algebraic structure of I don't know, like differential geometry and of what actually matters, or something along the lines of dynamical systems, because I was particularly interested in the fact that dynamical systems generally being described as continuous processes, like the same discrete to continuous thing might hold. This, like continuity might impose a lot of restrictions on the type of dynamics you can have, and discreteness might allow you to have more freedom to be specific. And I had like ideas of using algebraic topology to like scope out some essential features of like how algebraic topology is used to scope out essential features of manifolds, how algebraic topology might be useful to scope out essential features of dynamical systems. You know, I don't know if that's been done or not, but something along those lines.
Yeah, absolutely. And I think that's a really, in relation to the dynamical systems point, I think that's a really important general point that I at least feel has been underappreciated in general, which is that I'm going to pose this in an intentionally provocative way. But so I will go so far as to claim that every continuous mathematical structure can be obtained as a limit of some discrete mathematical structure. But there are many, many discrete mathematical structures that cannot be obtained as discretizations of continuous ones. And that this, in some deep sense, is why why we say that taking a continuum limit is such a restrictive process, as you put it, right? So you start with some multi-way states graph or something, and then you say, okay, I want the continuum limit of this to be some continuous phase space. The statement that it should be a continuous phase space is a huge restriction on the class of permissible dynamics. But starting with a continuum phase space and saying, I want this to be described, I want this to be discretized in such and such a way, is barely a restriction at all. And so, and I don't know, my like quasi-philosophical claim would be, as I say, that somehow that you can deduce any continuous mathematical structure as the limit of a discrete one, but you certainly cannot deduce every discrete structure as a finitary discretization of a continuous one. And again, I suppose one broader goal of the infrageometry program might be to try and see if we can make that statement a little bit more precise and potentially even render it provable in certain restricted cases.
Also, there's another, I mean, based on what you said, there's another idea which just popped in my head. I mean, it had been there with me for a long time, but I don't know if it's related or not. If you remember the subset construction, you basically have an MFA, you can get a DFA.
Yep.
Where essentially you just collapse, or I mean, you just take the power set as the new set of states. Right? So,
right.
Like, I don't know, it seems as if non-determinism is like when you zoom in and look at the underlying something, discrete structure or something, and then determinism comes in where you zoom out and look at the continuous structure. Or like,
well, I mean, I've always viewed. I mean, my position is that the Rabin-Scott theorem is one of those bits of theoretical computer science that has very, very profound philosophical implications, but that are kind of dramatically underappreciated. And for me, the main takeaway from the Rabin-Scott theorem is that determinism and non-determinism are not properties of systems, right? That they're properties of models. So I think if you learn nothing else from the power set control or the subset construction, as it's sometimes known. It's that basically you can take although it's described in terms of NFAs and DFAs, you can see the argument is in fact much more general, that in general, you can take any supposedly non-deterministic model and you can recast it as a deterministic model of the same process whose state space is the power set of the original state space. And so really what I think that tells you is that if you're just trying to model phenomena, you get to choose whether the model you use is deterministic or non-deterministic. That you can always have a non-deterministic model that's more minimal, that requires a smaller state space, that has fewer parameters, but you can always simulate that with a deterministic model that's larger, that has more parameters, larger state space. Which is why, when people ask, is such and such a system deterministic or non, is the universe deterministic or non-deterministic? Is quantum mechanics deterministic or non-deterministic? I kind of think that's a meaningless question, right? That you can model the universe in ways that using deterministic models, and you can model the universe using non-deterministic models. And if we learn nothing else from the Rabin-Scott theorem, it's that there's no fundamental distinction between the two. And it's the same thing I would say to discrete and continuous, which is what we were describing before, right? That somehow if you're restricted so that the only observations you can make involve discrete computable data, then again, whether you choose to model reality as being discrete or continuous is that's entirely your choice, an arbitrary choice. It doesn't really matter in some sense. So I would say that's that's kind of that's one of the overarching philosophical themes that we're kind of uncovering here. And I guess the point, or the point of relationship with the Infrageometry program might be that, ultimately that there's just more room with discrete representations. There's a higher diversity of structures that you can investigate with discrete representations, precisely because somehow discrete mathematical structures subsume continuous ones, because you have this operation of taking limits. But there are also many other examples of discrete structures that don't have obvious continuum analogs. Anyway, yes, many fascinating questions to explore in subsequent streams. So I think we have a course, well, at least a preliminary course, more or less charted for our next Infrageometry stream. When do we want to? Do we want to do that? Do we want to go back to doing those on Tuesdays, or do we want to keep them on Wednesdays? What are people's preferences? Carlos, Carlos, would you be okay with going back to doing Tuesdays, or should we keep them as Wednesdays? What do you think? Carlos, you're muted, right?
Sorry. Yeah.
Okay.
Yeah,
if you were saying things before, we didn't hear them either. So
no. I know. So I didn't say anything. I just said that I'm going to Edinburgh next week to do this doctoral training thing. So Tuesday, I think, is going to be more complicated than Wednesday, because Tuesday is when the seminar is.
Okay.
So the logistics might be a bit more complicated because of the timing, but Wednesday around this time should be fine.
Okay. I mean, given that you're traveling, if you want to push the live stream to later in the week or even to the week after, that's okay too. But
I think
really up to you.
What I might appreciate is having it 1 hour earlier. If that's feasible.
Yeah.
So, and then Wednesday, so maybe Wednesday at 1 hour earlier, so that would be 1700 UTC, like 5 p.m. UTC, I think. If we are all happy with that, I'm happy to put that in the calendar.
Yeah, that sounds good to me. Wednesday, 4th of October. Yep. Cool.
Although I need to make sure that I should be able to stream from the laptop, but yeah.
Okay. Look, as I say, if it ends up, if you figure out that it's too complicated or whatever, then I think it's not disastrous if we push it.
No, it should be fine. It's just that here I have control over everything. I'm sort of answering the chat at the same time, sending the links and everything. I won't have such a fine control then because I'll have a single screen, but it should be fine. Yeah. No
okay.
problem. Okay. I don't want to delay it one more week. Just it's too exciting.
That's fair enough. Okay, so the audience expect a potentially lower production value stream next time, maybe. They
shouldn't really get any difference on their end, but it's mostly my sort of agency over the state of the stream than the viewer experience.
Fair enough. Fair enough.
All right. So yeah, that was a real pleasure. I'll see everyone who's online next week, and I just shared the link to the community. There were a few questions that were a bit off topic, so very glad to see that discussion going. But if you want to continue it, please join the Discord. So follow that link and click on the Discord link. There's over there, and yeah, we'll see you in future streams and on our community.
Yeah, and actually on that topic, I mean, we will soon, as we gear up for our Institute relaunch, which will be in, it looks like it'll be in a few weeks. We will start doing, we'll start ramping up our live stream schedule, and in particular, we will start doing kind of regular community Q&A streams.
Yes.
So if you have questions, post them on the Discord. We're happy to answer them. If we don't get to them, or you're not satisfied with our answers or whatever, feel free to save them up, and we'll get to them in a future Q&A session that will happen hopefully very soon.
Yep. Absolutely.
All right. Well, thanks everyone for coming. It was always a pleasure. Thanks Carlos for presenting, and thanks Uti for asking great questions. This was really fun.
Yeah, thanks, Carlos. Your presentation was really nice on data derivations. Thanks, Jonathan. Thank you everyone for the infra calculus stuff. It's pretty fascinating.
Yeah. Exciting stuff. See you all next week.